Thanks for coming. So I will be talking about random Cayley graphs. And this is a topic motivated by the study of expanders and by some questions in information theory and also in additive number theory. And I'll try to explain the motivation. And please do not hesitate to stop me whenever something is not clear. Now, I should point out that already in this slide something is not quite right, in the sense that the Petersen graph, which is the one that you see here, is actually not a Cayley graph. But indeed, one thing that I want to show is that there is some difference between Cayley graphs and between general, say, regular graphs. Okay. So okay, so I'm not going to assume anything. You probably know the definition of a graph, but this is two sets notation. So all my graphs will be finite, and I denote a graph by an ordered pair, VE, where V is a set of vertices, so it's a finite set. And D is a set of pairs of vertices that are called edges. And such a graph is a Cayley graph of group if the elements of the vertices of the graph are all the elements of a group. So it will be a finite group in our case. And we have some subset of the group, S. And this subset will be closed under taking inverses. So S is a okay. So F is actually equal to S minus 1. And two vertices A and B are adjacent if A times V minus 1 lies in S. And because S is closed under taking inverses, this is if and only if B times A minus 1 lies in S. So indeed, this is an undirected graph. And here you see an example. So here the group is the cyclic group with 5 elements written additively here. And the generating set S consists of plus and minus 2. Right, so two elements are adjacent, even only if the difference between them is 2 or minus 2. Okay. So this is the Cayley graph. And one theme, I'm trying kind of to waste time because I see that people are still coming in. So somehow I want to not to really start before. Anyway, so one of the main themes is that that maybe it's interesting to study random Cayley graphs per se. And the reason is, so random graphs have been, and especially binomial random graphs, so this is a Erdős-Renyi model introduced some 50 years ago. So these have been very successful in proving that graphs with certain properties exist, in the study of problems in percolation, in the study of other problems. And there are many models of random graphs, and I wrote here binomial random graphs, random regular graphs, small world networks, random leaves, and there are more. And I think it's interesting also to study random Cayley graphs. And as I'll mention, some special properties of them have been considered quite a lot. But maybe it's useful to do it in a more systematic way, to really study the behavior of all interesting graph invariants for random Cayley graphs. And today I'll focus mostly about the chromatic number, which is a graph invariant that is studied quite a lot in discrete mathematics, in computer science also. But it's definitely interesting to study other properties of random Cayley graphs as well. So just to give you some motivating questions to show that the results here are somewhat unexpected, I have some, okay, but first maybe I'll say what is the definition of the chromatic number of a graph. So this is what is written here. So we denote it by chi of G, that's the chromatic number of a graph G. And this is the minimum number of colors required to color the vertices of G, so that adjacent vertices do not get the same color. and you see here a 3 coloring, a proper coloring of the Peterson graph. So the chromatic number of the Peterson graph is at most 3 because of what's written here, and is at least 3 because it contains an odd cycle, and therefore its chromatic number is 3. So I want to focus on the study of the chromatic number of random Cayley graph, and I'll tell you why I want to do it. But before that, I want to give you some motivating questions. So here is a specific question. Suppose n is, so the number you see here is just the biggest number I can write in PowerPoint. So n is bigger, suppose it is bigger than 10 to the 10 to the 10 to the 10. So it's some big finite number. And we take a group of order n. So now I didn't specify the group, it's just some group of large order, finite group. And we choose a random subset of it, of size big but small compared to the size of the whole group. So in the example here, it's of size 10 to the 10. And then I add to S the set of all inverses, S minus 1, because I want to get a set that is closed under taking inverses. And I look at the corresponding Cayley graph, and I ask myself, what is the typical chromatic number of this? Is it, for example, bigger than 10 with high probability? Yeah, so as I said, at the moment I still didn't specify, but soon I'll write here several examples for H. So okay, so it's a good question, but let me. So indeed, it will turn out that it depends on the specific group H. Later in the talk, I'll always talk about some specific group. So I'll have a group that I know what it is, and okay.
So this is something we understand if it was a random regular graph of this degree.
That's right. Yeah. So for example, a random regular, just a random regular graph of this degree would have chromatic number roughly 10 to the 10 divided by the log of this. So it will have a chromatic number, because it's known that a random d regular graph has, with high probability, chromatic numbers that is essentially d divided by the logarithm of d. Okay, and we want to know, to compare it with this case.
Independent of the size of the group?
Okay, so far I said independent on the size of the graph. So because of what Avi said, I switched for a second to random regular graph, not random Cayley graph. Okay, but now, okay, so this was only a comment in brackets. But let's now get back to groups. So we are asking about groups, and here are some answers. So the claim is that with high probability, and with high probability, let's say now, usually it means with probability that tends to 1 when some parameters tend to infinity, but here things are finite, so think about high probability, just probability 99%, 0.9 if you want. So the following holds. If a group H is an elementary abelian 2 group, so just binary vector of length k with respect to addition, modulo 2 in each coordinate, then with high probability the chromatic number is 2, exactly 2. Okay, so, now if the group is a cyclic group of prime order, so ZP, and again P is big, so the parameters are what we said before, then with high probability the chromatic number is 3, exactly 3. Okay, it is a. On the other hand, if the group is a more random-looking group, so what I wrote here is a modular group, so SL2ZP is a group of 2 by 2 matrices over the finite field with P elements and determinant 1, then I don't know what it will be, the chromatic number, but definitely it will be bigger than 10. So it will be bigger. So what this says is that indeed it matters which group we are choosing. Right? So at least for this range. For permutation group, yes. So it's a good question. I'm not sure. I think it will be closer to what happens in 3, but this will be mentioned in the open problem at the very end. So it is okay. So this is still one example. Yeah, in ZP to the k, it will be like this. So it will, yeah, if you ask enough questions, I'll not have to show anything. I'll just answer as said, because I'll, yeah, probably. Now here is another one. So what I wanted to show is that it's kind of hard to guess what will be the answers, and here is another one, which I think is also hard to guess. So suppose indeed it's the elementary abelian 2 group. I think that's a group that is easiest to understand, right? So just binary vectors of length 1000 here with respect to addition modulo 2 in each coordinate. And in the example here, I choose a random subset of 2700 elements. So this is just a case for which I know the answer. What is the typical chromatic number of these? And here the answer will be, and again, I think it's not easy to guess. So the answer is that with high probability, the chromatic number will be 4, exactly 4. And I thought it's remarkable, so I added an exclamation mark, and then I worried that the 4 would look like 4 factorial, so I took it one line down. But this is okay. Now I should say that despite what these examples may indicate, really we know very little about what's really going on. So these are very few examples where I can tell you what happens with high probability, but normally for essentially all groups and most interesting ranges of the size of this random set of generators, then we will only know to say very rough bounds about the behavior of the chromatic number. So these are really only few examples where, yeah.
You know worst case behavior?
So worst case, you mean if I try to make the chromatic number as big as possible? Yeah. So it is easy to always make the chromatic number the cardinality of this S plus 1, because I can just choose it so that it will contain a clique of size S plus 1, a complete graph of size S plus 1. And a graph with maximum degree D cannot have chromatic number bigger than D plus 1. So the worst case choice is always, assuming this was a question, right?
Yeah, but if it's a cyclic group, then you can't do that.
I can always choose the clique. So I want to have a clique in the cyclic group on the elements 1, 2, 3, 4, 5, 6.
Oh,
So I choose S to be 1, 2, 3, 4, 5, right? So I can always do it, but yeah, usually it's all right. So, but we definitely are interested in the random case.
The measure is always uniformly at random in the baseline.
Right, yeah. So I'll mention it in a minute. Okay, let me. So it will not matter much because the gap between the lower and upper bound of what I know are far enough so that the model will not change very much. But let me mention it. So here is a general problem, and then this question of Emmanuel comes naturally. So we have now, you can guess what is a general question. We have a given finite group, so now we know what it is. It's H, some group. And we choose some number S between 1 and, let's say, the cardinality of the group over 2. And then we choose a subset, a random subset of H of cardinality S. And it will not matter so much for me, so you can either choose uniformly among all sets of cardinality exactly little s, or choose with replacement little s elements. So it's not exactly the same model, but somehow, as I said, what we know about the behavior is not accurate enough to tell the difference between these two models. So think about the model that you prefer. Now we add to S the set of all inverses, S minus 1, because we want to get an undirected graph. And we get a corresponding random Cayley graph. So just reminding you, the vertices are the elements of the group H, and 2 are adjacent, A, B is an edge, if and only if A times B minus 1 belongs to S, or S minus 1. And then the chromatic number is a random variable, so we can ask about its expectation, about its variance, about its distribution, about its behavior. But I'm just asking here, what is a typical value? So I would want to know a typical value up to a constant factor or up to something. So how does it behave? Okay. And I'll tell you 3 motivations. So I'll not say much about each of them unless you will ask me, but on each of them I can say more. So the first one, put all of it. So the first one has to do with expanders. So expanders are pseudo-random graphs. So they are sparse graphs that are very well connected. And they have lots of applications in computer science, in combinatorics, in group theory, in other areas. And some of the best constructions of them, and they are best in some well-defined way, they are all the examples are Cayley graphs, basically. And the best known ones are the examples of Lubotsky-Phillips-Sarnak, independently by Margulis. The best explicit constructions, right, yeah. Yeah, okay, so now I talk about, so that's a reason for talking about Cayley graphs, but we want to talk about random. So why random? Actually also random, so there is this, something we proved with Yuval Roichman a long time ago, is that for every finite group, if you choose any finite groups that you want, if H will be the finite group, and you take the Cayley graph of H with respect to, say, 2 log H random elements in it, then with high probability this will be an expander. Okay, so again, I didn't define exactly what expander means, but it will. So it means that random Cayley graphs are indeed with high probability expanders. And more recent results are, so specifically I wrote here the result of Bourgain and Gambord. There have been several extensions to other groups, but says that if we take groups like SL2ZP, so 2 by 2 matrices over ZP with determinant 1, then here if you choose randomly even a bounded number of generators, 10 generators randomly, then with high probability this will be an expander. And as I said, something similar holds for other groups, like I wrote here the result of Rouillard, Green, and Tau. This is about Suzuki groups, and there are other as well. Now you see, to be highly expanding, so an expander is a graph in which every set has lots and lots of neighbors outside the set. If it is a very good expander, then it doesn't have a big independent set, because an independent set, all the neighbors are outside the independent set. And if the independent set is big, then it means that it doesn't have so many neighbors. Right? So somehow if something is a very good expander, it means that its independence number is pretty small, and its chromatic number is pretty big. In fact, for Cayley graphs, or for vertex transitive graphs, independence number small and chromatic number big are essentially the same thing. So up to logarithmic factors, really the bound you get for the chromatic number from the independence number is always tight. So somehow it means that if we want to understand better the expansion properties of random Cayley graphs, it's similar to understanding their chromatic number. Okay, so this is one thing. The second motivation comes from information theory. So let me first say the buzzword, and then I'll say something about it. So it turns out that random self-complementary graphs, random self-complementary Cayley graphs of appropriate groups, they provide examples of graphs with large chromatic number and relatively small, something that's called Witzenhausen rate. So this is something in a paper with Alon Orlitsky, also a long time ago. And this Witzenhausen rate is something that arises in information theory. So let me tell you a little bit about that. So you can consider the following communication game. We have these 2 players that's customary to denote by Bob and Alice for A and B. So they know a graph G. Even before they start to play, they are going to play on some graph, and they know some specific graph G. And for some specific graphs, this communication problem comes sort of naturally, but let me just think about it as a communication problem on the graph. And now the situation is that Bob knows an edge of the graph. He is getting some edge of the graph, and Alice gets one of the endpoints of this edge. Okay, so she knows an endpoint of the edge, and she wants to transmit some information to Bob so that he will be able to tell which endpoint it is. Okay, and as is usually the question in information theory, we try to do it by sending the minimum possible number of bits. So this is written here. What is the minimum number of bits that Alice has to send to Bob so that he will be able to recover the endpoint? Now that's actually an easy question. And the answer for it is exactly the ceiling, because we want an integral number of bits, the ceiling of the log base 2 of the chromatic number of G. And this is why, because one thing they can do, Bob and Alice, they can decide about a proper coloring of the graph G. So they can fix some proper coloring and agree to play according to it. And then the only thing that Alice has to send Bob is the color of her vertex. Now, because this is a proper coloring, then the two endpoints of the edge that Bob has have distinct colors. So once Bob will get which color it is, he will know that it's this endpoint and not this, and not the other one, because they have distinct colors, right? And you can also convince yourself, it's essentially saying the same thing again, that this is the best that they can do, that the information Alice sends to Bob should be a proper coloring of this graph. Okay, so that's simple. But one main theme or common theme in information theory is that things become more efficient when communication becomes longer, or when we repeat things many times. So let's ask now what happens in the same game, on the same graph, if Bob now has two edges, E1 and E2. They have nothing to do with each other, so he just has two edges, and Alice has an endpoint of E1 and an endpoint of E2. How many bits does she have to send Bob now so that he will be able to recover both endpoints? So of course she can repeat the same thing twice, and she will have to send twice as many bits. But it turns out that in some examples at least, and specifically in random self-complementary Cayley graphs of high chromatic number, they provide examples where the number of bits she will have to send for one edge is roughly the log of the number of vertices of the graph. And also for two edges, she will have to send essentially the same. So she will have to send an extra 1 or 2 bits. Okay, so it's kind of whatever you do for one edge, you get already the second one for free in some of these examples. And more generally, the Witzenhausen rate is you look at the limit. Suppose they play on this graph, and B has many, many edges, and Bob and Alice has endpoints of each of them, and we ask how many bits she has to send per given edge in the limit when the number of edges is very big. So one can show that something here is sub-additive, and because of Feket's lemma, this limit exists. And this limit is actually called the Witzenhausen rate of the graph. And it's didn't hear? Is there anything? Is it related to the Shannon capacity? So it's quite related in the sense that the Shannon capacity is to the independence number of the graph exactly what's the Witzenhausen rate to the chromatic number of the graph. And because of this also there would be some bounds that, so this is always okay. But it's really, So the Witzenhausen rate is you take a high power of the graph with respect to the same product as in the Shannon capacity, and you color it, and you take the kth root or the logarithm dividing by k. This is right. So because of this question, I'm kind of, I hope that you hear me better than I hear Moses, but okay, if you don't, so tell me. So somehow it is a, so these random self-complementary Cayley graphs on n vertices, they provide examples where one edge requires roughly the logarithm of the number of vertices bits, and the Witzenhausen rate is at most half the logarithm of the number of vertices. And it looks interesting. So here is an open problem about this. There are many problems about this, just like the Shannon capacity. Very little is understood about this. But it's open in particular if there are graphs G on n vertices, where for one edge we'll need to send very close to log the number of vertices bits, 0.99 log n bits, let's say. But for many edges, we'll have to send only 0.01 log n bits per edge. And somehow maybe understanding better the chromatic number of this random self-complementary, in this case, Cayley graphs or maybe others, maybe we'll be able to say something more accurate about this. Okay. Now the third motivation, this was actually maybe my original one, has to do with additive number theory, specifically with sum sets. So, so in additive combinatorics, in additive number theory, sum sets have been studied a lot. So sum sets are sets of the form A plus A. We just look at all the Minkowski sum. So just a plus a is a set of all little a plus little a prime as a and a prime is in a. And somehow we want to understand the structure of this, or we want to understand which sets are some sets. I checked a few days ago in Math Reviews, in Math Scinet, there are 163 papers in which the word sum set appears in the title. And actually there are 53 more papers in which the word sum set also appears in the title, only it appears with one word with a hyphen between the sum and the set. So really this has been studied quite a lot. And here is one interesting result, first proved by Ben Green. So what he noticed, and it's not so clear why this is the case. So suppose we are in ZP, so just the additive group of finite field, or the cyclic group with p elements. Then if we take in ZP the complement of a small set, we delete just very few elements, then what we get is always a sum set. It's always of the form a plus a. Okay? So if you delete, if p is big, and you delete only 1,000 elements, then the complement is always of the form a plus a. And let's denote, so he denoted by f of p, this will be the maximum f, so that whenever we delete f elements from ZP, then what we get is a sum set. Okay? And we want to estimate this f of p, so he showed that it's at least some constant, 1 over 9, maybe log p. And with Gowers, he showed that it is not much more than p to the 2/3 plus epsilon. I could improve this bound, so indeed it behaves like a power, and this f of p is at least square root p over square root log p up to a constant, and at most p to the 2/3 over some log factor. And there are reasonably good reasons to conjecture. Let me not tell you the reasons, but the truth should be the lower bound, so it should behave like p to the 1/2 up to some logarithmic factors. Now, let me tell you something about why, if we would know the chromatic number of certain random Cayley graphs, this should hopefully prove this conjecture, if indeed the chromatic number is what I think it should be. So really the proof of the upper bound, so what is the upper bound? I have to show that we can delete not too many elements from ZP, maybe about square root p or about p to the 2/3, so that once we delete them, then what we get is not a sum set. It's not of the form a plus a. So this goes roughly as follows. We want to delete, to prove the existence of such b, we will choose b in 2 steps. First, we will choose half of it, and afterwards we'll choose the other half. So the first half we choose at random, or I mean, maybe we can do something more clever, but the only way I know to do it is to choose the first half at random. And then if we choose this set, half of the elements of b at random, so we know that these elements are already in the complement of the sum set. So they should not belong to a plus a, okay? And that means that now a should be an independent set in what is called the Cayley sum graph of ZP. Cayley sum graph is almost like Cayley graph, only we connect two things if their sum belongs to this set b prime and not if they're difference, okay? So if I want a plus a to be disjoint from b, then a has to be an independent set in the Cayley sum graph. Now, if this Cayley sum graph has a small independence number, which for Cayley graphs, as I told you, because they are symmetric, it's essentially the same as saying that they have high chromatic number, then there aren't too many of them, just because there aren't too many small sets. So there are not too many possibilities for a, so that a plus a will be disjoint with b prime, which is half of the set b that we have chosen. And now if we don't have too many candidates a, then because there are many, many ways just by counting of completing this set b prime to a set b, we can add another half, then there are too many ways and we don't have enough a's, so for one of these ways to complete it, we will get that this is not a sum set. So this is simple. I don't know if it was possible to follow, but at least it gives you the flavor of things. So if we would know that indeed a random Cayley graph has smaller independent set than what we can prove for this random Cayley sum graph, or as small as I think it should be, then this would give the square root p in that question of green. Okay, so let's talk a little bit about the general thing. I'll tell you what we know and what we don't know. And, okay, so here is just some notation. H will be a group of size n, so finite group, and S will be a random subset of H of size, now denoted by k, at most n over 2, and I denote by chi of H and k will be the chromatic number of this random Cayley graph. So we said this is a random variable. We want to understand what is its typical value, and one thing that we could think is that is to compare it. So this was what Avi asked or mentioned at the beginning, to compare it to just random regular graphs, because of course the Cayley graph of G with respect to S union with S minus 1 is always a regular graph. And it's a regular graph of degree, which is roughly, well, degree is the cardinality of S union S minus 1, but we don't know exactly what's the cardinality of this set, right? Because it depends how many of the random elements were inverses of themselves, or maybe we chose them and we chose the inverse as well. And also it depends maybe if we will take the random set S with replacement or without replacement, but basically it's a regular graph of degree which is constant k. So between at most 2k and with high probability at least k minus a little bit. So the chromatic number of every graph with maximum degree d is at most d plus 1. So definitely the chromatic number of these is at most some constant k, or at most 2k plus 1 if you want. And the known fact about the chromatic number of random regular graphs of a given degree, actually more accurate results are known, but it is known that the typical chromatic number is constant k over log k. So it's not really the maximum degree or the degree of regularity, but we gain a factor of log. And maybe our initial guess would be that this chromatic number of the Cayley, the random Cayley graph of H with respect to k generators, random generators, will behave similarly. Although I told you in the beginning that there are some examples where we know that it's behave a little bit differently, but maybe still this would be a reasonable guess. So what is known about this? So here are some results for general groups. So suppose I don't assume anything about the group, it's just a finite group, and I choose a subset of size k and take the inverses, look at the Cayley graph. So the following inequalities all hold with high probability, and this is now for every group and for every k. So the chromatic number is always at most 3 maybe times k over log k. Namely, indeed, at least from the upper bound side, whatever we got for random regular, we get also for random Cayley graph. We gain this log factor with respect to the degree. What about the lower bound? So it's quite far. The lower bound, well, first, instead of log k, we divide by log n. We have to, right? Because, okay, we'll see. Because in some examples, indeed, when k is at most log n, then still the chromatic number is bounded by 3, like the examples we saw for cyclic groups. But anyway, so this is, instead of dividing by log k, we divide by log n, but what's worse, the lower bound is the square root of this thing. So there is really a huge gap between the lower and upper bound that you see here if k is in some middle range, when k is something like square root n, for example. Sort of, or and that I'm using expansion by using eigenvalues. Yeah. So it will. That's right. Yeah. So somehow we don't have a better way for general groups, at least. In fact, for any. Okay. So there is a big gap. I mean, for very big values of k. So what you see here is another lower bound, which does not give anything when k is smaller than square root n. Right. It is less than 1. But if k is very big, like k can be n over 2, for example, then this lower bound is better, so it's k squared over n log square n. In particular, you see that if k is n over 2, if it's like the random graph gn 1/2, when we choose half of the elements, then really a lower bound of the chromatic number is n over log square n, and upper bound is n over log n. So at least for the dense case, it's pretty close, upper and lower bound. But in the middle, there is a very big gap, and in fact, the middle seems to be the most interesting case. So it will be nice. Yes, so again, this will come at the very end, but one of the questions is that always it should be k up to polylog in n, maybe, right? So that could be true. I'll mention it again at the end. So yeah, so probably, or the guess would be that the upper bound is somehow closer to the truth than the lower bound, at least for big values of k. Let me tell you something about some specific groups. Okay, and I wrote here, so special cases. So actually the case when k is n over 2 was considered in several papers, so in the two papers that I mentioned before, in a more recent paper by Christofides and Markstrom. Here is another example that I mentioned before with a specific parameters, this 10 to the 10 to the 10 to the 10. So really, if we look at the SL2 ZP again, modular group, so 2 by 2 matrices over ZP with determinant 1, if we choose k generators at random, then the chromatic number starts increasing immediately, but we don't know how, so it is at least k to the delta for some fixed delta. Delta is 1 over 20, maybe, something. But it means that already for k, which is a billion, then already this starts to be big, even if p is very, very big. This would follow, right? Yeah, I would mention it if I would have right. Here is something specific about groups of prime order, so cyclic groups of prime order, ZP, like I mentioned before. So there is a relatively recent result by a young Polish mathematician called Czerwinski, shows that for k up to something, log p over log p to the 1/2 is what follows from his proof, then the chromatic number of ZP with respect to k random generator is at most, and therefore exactly 3. You see, it is at least 3 because p is odd, so once we have a generator, we have an odd cycle, and it stays 3 for a while. And I could show that for a while is for a while longer, right? So for every k up to 1 minus epsilon, or 0.99 log by 3 of p, then really the chromatic number of ZP with respect to k random generators is at most 3. And note that indeed immediately after log p, so I'm not sure about the constant here, but right after log p, the chromatic number starts increasing, right? Because we said that in general, the chromatic number of every group, and in particular of ZP with respect to k random generators, is at least constant square root p over square root log p. So once k will be big constant times log p, this will start growing. So for a while it stays 3, but then it starts growing. And something similar, actually I didn't write it here, but something similar holds for any cyclic group. In fact, something quite similar holds for any abelian group. And still for ZP, so if we take bigger k, then with high probability the chromatic number is at most k over log p. So we gain this log p at the beginning, and afterwards it stays, at least the upper bound stays k over log p. So when k is like 1,000 log p, then the chromatic number is at most 1,000 something. And then there is a result by Green, and a more recent, more accurate result by him and Morris, that for k which is really constant p, so for very dense graphs, then the chromatic number of ZP with respect to k random generators is indeed constant p over log p. So maybe we don't know the exact constant. I think that here it's even possible to get the exact constant, but it means that at least for ZP, really in the dense case, things behave like a usual random graph. So the usual random graph G n 1/2, the chromatic number of it is n over log n with high probability, n over 2 log n, and the same holds for this random Cayley graph of ZP. This is not exactly the case for other groups, but it is kind of similar. Okay. So I'll say there are a few more examples where things are known, but I want to tell you something about the proofs, not too much. So kind of naturally, the proofs will be partly combinatorial because we have graphs here, and partly probabilistic because we have random graphs, and partly algebraic because we have Cayley graphs, right? So the algebraic part are mostly indeed spectral techniques, so just it will be convenient to use information we have about the eigenvalues of the adjacency matrices of graphs and the known connections between the structure of a graph and its spectral properties. And the combinatorial and probabilistic arguments will be different. And I want to say something about the probabilistic. So one example of a probabilistic proof I think is interesting. And I'll not really show it, but I'll kind of show enough of it, I think. And this has to do with groups of prime order. So you know that when you prepare a lecture with PowerPoint and you want a picture, you go to Google Images and you write, here I wrote groups of prime order. You get a picture. Usually you have no idea why this picture is related to a. But here actually I thought about it. So it's a group of people and there are 7 of them. So that's a prime. So probably this is, but anyway, this is, okay. So here is a. We want to prove the following. So we want to prove that if we have ZP, so think now about P as some large prime, right? And we choose 0.99 or 1 minus epsilon log by 3 of P random elements of ZP, and we take them, we take the inverses, and we want to show that with high probability the chromatic number is 3. So what we will show is the following. That's very intuitive, I think. So we'll show that with high probability for random x1, x2 up to xk, so these are the random generators, with high probability there exists some A, this red A in ZP, so that if we multiply AXI and we compute it modulo P, then all of these numbers lie in the middle third, between P over 3 and 2P over 3. Okay, so we will show this, or I'll say why we should believe it's true, and not quite show it. But let's say for a minute believe that this is the case, then let me, what? No. So this is definitely not pigeonhole. So it looks indeed somewhat similar to these Dirichlet things, right? That, but see, the Dirichlet thing tells you that for any x1 up to xk, you can always multiply them by A modulo P so that all of them are small. But to get things in the middle third, usually you will not be able to do it. For example, if you have 1 and 2 together, you will not get both of them in the middle third. So here it's only something that holds with high probability, but we'll see. Okay, now let's first see why this will be good. So this is very simple, that once we have this, we'll get the coloring. So here is how we get the coloring. We'll take ZP and we'll cover it by 3 cyclic intervals of essentially equal size. So each of them is of size about P over 3. Okay, so we'll cover it. And then we will color each element y in ZP by the index of the interval containing AY modulo P. So we have this A, so that AXI modulo P is in the middle third for each of our xi. And now if we want to color y, we just take y, we multiply it by A modulo P, and then it falls either in the first interval or the second or the third. It doesn't matter so much where they are located. We just covered it. They are all of size about P over 3, and they cover everything. And the index of the interval tells us the color. Okay? Now, why is this a good coloring? So that's simple to check. So suppose y1 and y2 have the same color. What we have to show is that their difference is not plus or minus xi, because that's the definition of the Cayley graph, right? But you see, if they have the same color, then it means that AY1 and AY2 modulo P, they both fell into the same interval. And because of this, the difference between them is small. I mean, they are in the same interval, so the difference between them is strictly between minus P over 3 and P over 3. And because of this, the difference between them cannot be in the middle interval between P over 3 and 2P over 3, so it cannot be plus or minus AXI. And that means that they are not connected, right? Because if the difference between them would have been plus or minus xi, then after we multiply by a, the difference between them would be plus or minus axi. Okay. So it will be enough to prove these. So again, what we want to prove now at least explains why we get the log and the log by 3. We'll soon see. So what we want to prove is that once k is at most 1 minus epsilon log by 3 of p, and we take k random elements in ZP, then with high probability there is an A, so that AXI modulo P is in the middle interval for all of them. Okay, why we should believe that this is the case? So the intuition is very clear, I think. You see, if you fix an A, so fix some A, and let's compute the probability that this A will be good for us. So what is this probability? So once A is fixed, then the probability that AX1, for example, modulo P falls into the middle third is 1/3, right? So roughly, I mean, P is not divisible by 3, but whatever. So it's 1/3, and the xi's are random and independent, so the probability that all of them, for all of them, AXI lies in the middle interval is 1/3 to the k. Now, because k was 1 minus epsilon log by 3 of P, this 1/3 raised to the power k is still bigger than P to the 1 minus epsilon. And therefore, we expect the expected number of A's, which are good for us, is P minus 1 by linearity of expectation divided by 3 to the k, which is bigger than 1, much bigger than 1. Right? And because of this, we expect to get some A. But of course, this is only an intuition, because the fact that a random variable has big expectation does not necessarily mean that with very high probability this random variable is positive. And indeed, we have to do something because things here are not independent. So there is some trick to, and I kind of wrote it here, but I'll not, let me not show it. So there is essentially a trick to not to compute AXI modulo P, but to add also a y, and to compute sort of AXI plus yi, although this is not what we want. But once we do that, then we get pairwise independence. So I'm just, and once we get pairwise independence, then we can apply Chebyshev and then get some bound for the probability. And then there is some trick that you can just kind of sketched in the few transparencies I didn't show you, that enables you to get rid of the y's afterwards. So it's just to say that there is some way to add something and delete it, and still it would work, and then one can apply second moment, and it works nicely. So this is how you prove the result for cyclic groups of prime order. The same holds for cyclic groups of non-prime orders, only there the computation gets more complicated. We don't get pairwise independence. We have to estimate some covariances. It leads to some problems in number theory, but one can do something. Anyway, so let me say something about general groups. I'll just say what is the basic spectral idea, which is simple, but let me do it anyway. And then I'll mention some open problems, and that's it. So one of the lower bounds that was true for every group is that for every group H of order n, and for all admissible values of k, we said that with high probability, this chromatic number of H with respect to k randomly chosen elements, and their inverses is at least constant square root k over square root log n. So we want to prove it using the spectral properties or the eigenvalues of the adjacency matrices of these random Cayley graphs. So we have many experts in eigenvalues of random matrices. from the audience. So no, so right. So this is a okay. So so simplest is to use again this paper with Reuschmann that I mentioned at the beginning. So what we showed there is the following: that for every k which is bigger than log n, then if you look at the eigenvalues of a random Cayley graph of H with respect to a set of k random generators, then all the non-trivial eigenvalues, so every d regular graph, the largest eigenvalue is always equal to d. So here the largest eigenvalue will always be equal to a k, constant k, depending on the cardinality of S union set of inverses. But the absolute values of all the others will be much smaller if k is somewhat bigger than log base n. Namely, the absolute value of each other eigenvalue with high probability is most constant square root k square root log n. And there are several subsequent proofs of these results that give some somewhat better estimates or some, somewhat better way to look at it. And the estimate is still the same, essentially. And then there is an old result of Hoffman. Actually, it proves something much more general, but this is what it gives if you plug it in the case of regular graphs, which is simple. And this is the chromatic number of any d-regular graph with smallest eigenvalue lambda. Now, the trace of the matrix of a graph is 0 because we don't have loops. So we have so the smallest eigenvalue is negative always. So the smallest means the most negative. So the most negative eigenvalue is lambda. Then the chromatic number is at least d minus lambda divided by minus lambda. Minus lambda is positive, right? So the number you see here is positive, and basically it's the ratio between the degree of regularity and the bounds that we have for the absolute value of the most negative eigenvalue. So if we divide k by square root log n, we get this bound, which is square root k over square root log n, and exactly the same would follow for this SL2ZP if we want, by taking the result of Houdin and Gumbord. So really they prove that this random Cayley graph of SL2ZP are good expanders, again by looking at the eigenvalues of the adjacency matrices. And if you follow what's in the proof, then it basically tells you that all the non-trivial eigenvalues of random Cayley graphs of SL2ZP with k generators are at most k to the 1 minus delta for some specific delta bounded away from 0, and you plug it in the same bound of Hoffman. Okay, so let me just finish with some problems. So indeed, you can ask what is happening. You asked already what is happening for other groups, and maybe the most natural one to look at is the symmetric group. So just I think that the symmetric group should behave roughly like this SL2ZP, like those finite simple groups, but they don't know. For a while, I thought it should be possible to prove that for solvable groups, say H. So I told you that for any abelian group H, it is true that the chromatic number does not grow. So for a while, it stays at most 3, even when the number of generators grows up to some constant log. And hopefully, this should be true for any solvable H. I don't quite see it even for nilpotent, but anyway, so if I would have to guess, it should be true. Now, the groups that you get the impression that you understand best, I said it already, are the elementary abelian 2 groups, so binary vectors of length t with respect to addition. Here, so let H be this Z2 to the t, the number of elements is 2 to the t. If k is n over 2, so we really choose half the elements, here every element is the inverse of itself, we don't have to add the inverses, then one could show that indeed with high probability, the chromatic number is up to constant n over log n log log n. So it does not behave here exactly like in a random graph. There is this extra log log n factor, And this is because these groups have lots and lots of subgroups. So unlike ZP, it doesn't have subgroups at all, and because of this you gain something. And also one can show, and this depends on something else, but this explains the examples that I told you at the very beginning of the lecture, that if k is between 1 plus epsilon t and 3 minus epsilon t, so I wrote here 1.1 t and 2.99 t, then with high probability the chromatic number will be 4, exactly 4. So not right. And but again, it will be interesting to understand what happens if the number, if k is square root n, and then I don't know. In fact, if k is about square root n, I don't know for any group. Actually, that's the last problem. And this is, I think, what Emmanuel asked at the beginning. So it should be true, although we have seen that some groups behave differently than some other groups when k is relatively small, and differently than random regular graphs, it still could be true, and I think should be true, that for every group H of order n, and for all admissible value of k, if we don't care about logarithmic factors in n, then this chromatic number of H with respect to k random generators is essentially k, so up to some logarithmic factors. In particular, if k is square root of the size of the group, then it should be roughly the square root of the size of the group, the chromatic number. But not only we don't know this, I don't know it for any group whatsoever. So you are free to choose any infinite family of groups that you like, and prove something like this for all the interesting range of k. That would be very nice. So with this, I'll finish. Thank you.
Thank you very much. Time for some questions.
Okay.
Is there a notion of